Today we're going to be using acid strength to predict the direction of a reaction. So if you're having trouble writing the proton transfer reactions, you might want to go back and look at day one. Okay. We're also going to explain the process of neutralization and describe it chemically. And then we're also going to describe self-ionization of water. So the first thing that I'd like you to do, and I'd like you to pause and give this a try, identify the Bronsted-Lowry acids, bases, and we'll stop there. If you can do the conjugate acid and the conjugate base based on your reading, that's fine. Go ahead and do it. But for now, let's just do Bronsted-Lowry acid and base. So when I look at this, okay, what's happening is that this perchloric acid is donating a proton, so it's proton donor, to water, which is accepting that to become hydronium, and that leaves perchlorate ion, which means that this is our acid, and this is our base. Okay, now what if I do this? What if I put this arrow here? That means that the system's at equilibrium, right? So now let's think about the reverse reaction. Well, in the reverse reaction, hydronium ion gives its proton to perchlorate ion to become water and perchloric acid, okay? Which means that in the reverse direction, this is a proton donor and this is a proton acceptor, which would make this an acid and this is a base. Okay, now you'll notice some things here, all right? So the base acid, these two things are related, right? So the base molecule kind of is water, and then these two are related, the base being kind of this perchlorate ion. So we call both of these conjugate pairs, okay, conjugate pairs. And what we say is that the conjugate of an acid is a base, which means that this is going to be a conjugate base. And that would make this a conjugate acid. Okay? So let's start working our way through this, and hopefully you'll see the pattern. And when you start to see the pattern, why don't you pause the video and fill out the rest of the table, okay? So here I have nitric acid, which I'm saying is a strong acid, okay? On this side, I'm asking for conjugates. So the conjugate of this strong acid is NO3 minus. Now, how did I get that? Well, I'm saying that this is an acid, which means that in a reaction, this nitric acid is going to donate its proton, okay? When it donates its proton, it's going to form NO3 minus. And we would call this a weak base. Okay? Now here's hydrogen sulfide ion, okay? This is a weak acid. Now, I'm still saying that it's acting as an acid, which means it's going to donate a proton, which means its conjugate base is going to be S2 minus, okay, because it gives up another proton. And this, the conjugate of this, S2 minus, we're actually going to call this a pretty strong base. All right? Here's hydrogen carbonate ion, which I'm saying is a weak acid. So again, we're donating a proton, which would make the conjugate base CO3 2 minus, and that is a pretty strong base. Okay, here's hydroxide ion. It's a strong base, which means that it's going to accept a proton coming this way, which would make its conjugate acid, HOH, also known as water, woo! And we'd call that a weak acid. super weak acid. Okay? Here's chloride ion. It's a weak base, so it's going to be a proton acceptor. That's going to make the conjugate HCl, which is a strong acid. And this last one, HPO4 2-, I'm saying this is a weak acid, which means it's going to donate a proton. Now notice that I did something a little tricky here. That would make this PO4 3-, which is a strong base. All right, so aside from getting comfortable with the proton transfer and the conjugate pairs, one of the things that you can see here is that the conjugate of something strong is weak, always, okay? And the conjugate of something weak is strong, always. There you go. So that's good information to have in front of you. Okay, so as it turns out, this isn't just like binary, strong or weak. There's a whole table, okay? There are whole shades of gray here. So once again, pull up this acid strength chart, okay? And we'll see our strong acids up here and H3O+. Moving on down, we said that water is a very weak acid. And then, so notice that acid strength increases going this way, base strength increases going this way. And notice that whatever this is the conjugate. So the conjugate of a very strong acid is a very weak base, okay? And you see the kind of relationship there. All right? All right. So how do we use this to predict the direction favored by equilibrium? Okay, well, let's go through and let's label all of, let's go through and let's label all of the acids and bases in this first one. All right, so I know that this is an acid, and this is a base, and this is an acid, and this is a base. Okay, so now all of these things are in solution at the same time, right? So if I have two acids, the stronger of the two acids is going to be able to give up its proton and be an acid, okay? So think about it as like a sumo wrestler versus a sixth grader, okay? The sumo wrestler is stronger, so they're going to be able to do whatever they want to do, and the sixth grader won't be able to do what they want to do, okay? So if I look at my acid strength table here, all right, and I find HClO4, which is a very strong acid, so here it is right here, and I find water, hydronium ion is my other acid, H3O+, okay? HClO4 is stronger than H3O+, which means that this acid is stronger. All right. Now the bases, I'm comparing H2O and ClO4-. So here's ClO4-, it's a very, very weak base, and here's H2O. It is also a weak base, but it's not as weak as ClO4-, all right? So H2O is actually the stronger base, all right? Which means that equilibrium favors products because these stronger things are able to accomplish their tasks. So the stronger acid is able to donate its proton, and the stronger base is able to accept the proton. So it drives it that way. Now notice that by that rationale, it's unlikely that you're going to have a strong acid and a strong base on the same side. On opposite sides. All right, you just got to keep that in mind. Now, the reason that you're not going to have that is that this all works on conjugate pairs, right? You couldn't have the strong acid on this side and the strongest base on this side because the conjugate of a strong acid is a weak base, all right? Now, I could do something along the lines of which of the perchloride ion containing species, and by species I mean things, okay, has the greatest concentration in solution? Well, we know that equilibrium favors the products, which means that perchloride ion, the concentration of perchloride ion at equilibrium should be greater than the concentration of perchloric acid. Easy enough, right? Why don't you pause the video and try this yourself with this second example. All right, so I have acetic acid and water, hydronium, and acetate ion. So this is an acid, this is a base, this is an acid, this is a base. All right, so what's my strongest acid? Acetic acid or hydronium ion? Well, here's hydronium. Okay, oh, there's acetic acid all the way down there. So hydronium ion is actually the stronger of the two acids. Okay, and acetate is going to be a stronger base than water. Okay, so equilibrium favors reactants. Okay, and which would mean that unionized acetic acid is going to have the greater concentration in solution. Now, a lot of these acids are water soluble, even if they're not dissociating. So oftentimes, we just call this the unionized acid. Every once in a while, you'll find an acid that's not soluble if it has a proton, but it is soluble if the proton's been donated. But that's a very odd case, so you don't really have to worry about that. Okay, so the unionized acetic acid in solution will have the greatest concentration. And notice that this is really what we mean by strong and weak acids, right? A strong acid is able to force equilibrium to products, so you're going to end up completely ionizing. Whereas a weak acid, you're going to get incomplete ionization, which means you're going to end up with a lot of the acid unionized with that proton on there in solution. It's going to be soluble, but it'll still just be in solution. Okay, that's important stuff to keep in mind. All right. So here I have an example of a strong acid reacting with a strong base. Okay. And this is an example of a neutralization reaction. Okay, a strong acid reacting with a strong base, and they're going to produce a salt and generally water. Okay, the hydroxides will produce water, and as I'll show you in a little bit, the amines won't. All right, so one of the things that you're going to notice here, if I cover up this side, this is set up to do a double displacement reaction, right? So the cation from one thing will react with the anion from the other, and we'll get this. So HOH, which is water, and NaCl, which is going to be sodium chloride, which is going to be a salt. Okay, so this is the balanced chemical equation. What if I ask you to write the net ionic equation? Well, you should remember how to do that. And if you don't, maybe you should go back and watch the video about net ionic equations from the first semester, in fact. So this, being soluble, will dissociate into H plus Cl minus. This will dissociate into Na plus OH minus. Okay, this is soluble, so that's Na plus Cl minus. And then water is going to stay together as a pure liquid. Okay, so now if I ask you to find the net ionic equation, so this was the complete ionic, here's complete, woohoo, complete ionic. What about the net ionic? Well, the net ionic is going to be the formation of the product, which is H2O. This is H plus OH minus. Now, in your textbooks, okay, or on some problems, one of the things that you might have to keep in mind is that H plus is equivalent to H3O plus. But if I use H3O plus in this, if I use hydronium ion plus hydroxide ion, it's going to change the chemical reaction a little bit. All right, not a big deal, but it is there. All right, So that's bases that are metal hydroxides. Well, what if your base isn't a metal hydroxide? What if your base is one of the other types of strong bases that we talked about, which is the amine-containing bases? So that's HCl plus NH3. All right. Well, this one now we're using proton donation. All right. We really were up here as well. HCl donated its proton to the base in this compound, which was hydroxide. All right. So this is another proton donor acceptor reaction, okay, which makes NH4 plus Cl minus, okay? So that's just ammonium chloride, NH4Cl. NH4Cl aqueous. The next thing that I want to talk about is this kind of funny reaction here, all right? So water is interesting in that we know that water is amphoteric, which means that in a solution of water, you at any given time could have a water that's acting as a proton donor and a water that's acting as a proton acceptor. So see if you can use that information to finish this reaction. So pause it, see if you can get it right, and then see what I say. Well, if this water donates a proton to this, okay, what's going to be left here is OH minus plus the proton gets donated to here, H3O plus. And we call this the self-ionization of water. Water can ionize itself. Interesting, right? So the next thing that I want you to do is I want you to pause the video and write the equilibrium expression for this reaction. So KEQ equals concentration of H3O plus times concentration of OH minus. And notice that I don't put it over anything because these are both pure liquids. Oh, that's cool. Well, this is a special equilibrium constant because this is true for water. That is, we give it a special K, another K, which is KW. So KW equals concentration of H3O plus times concentration of OH minus. It's one of the equations on your equation sheet. Now, remember back to our days in equilibrium. I know it was all of like 2 weeks ago, but changing the concentration of one of these things doesn't actually change the value of KW. The only way that you can change this value is by changing the temperature. All right? So at room temperature, this always has the same value, which is 1.0 times 10 to the minus 14. Okay? That's cool. Now, what do you know about neutral solutions? And specifically, what do you know about the relationship between hydronium ion, H+, and hydroxide ion in solution? Hopefully you remember back to the days where you know that in a neutral solution, the concentration of hydronium ion has to be equal to the concentration of hydroxide ion. Okay, so if I make this X and this X, I could solve for X for each value, and that gives me X squared equals 1.0 times 10 to the minus 14. Here's me doing that math. All right. Square root of that, X equals 1.0 times 10 to the minus 7. Okay. So in a neutral solution, this is 1.0 times 10 to the minus 7 molar. Now, this is a molar. This gets a unit because these are concentrations, right? Well, what would we say about the solution if the concentration of H3O plus is equal to 1 times 10 to the minus 10 molar? Well, that's interesting. Okay, well, 1 times 10 to the minus 10 is less than 1 times 10 to the minus 7. Okay, so even though I give you information about hydronium ion concentrations. This has less hydronium than a neutral solution, which means that this solution here is basic. All right, well, that's interesting. What about if I say, what if concentration of H3O plus is 1 times 10 to the minus 5 molar? Well, now this value, 1 times 10 to the minus 5 molar, is greater than this value, 1 times 10 to the minus 7 molar. So we would say that this solution is acidic. Okay? All right. Now the last thing that we're going to do today is we're going to talk about the kind of math that you might do with this. Now, this is a lot of these are just kind of stoichiometry type problems that you've seen before, and really all that I'm doing is I'm adding the sort of acid-base nomenclature in, or acid-base reactions. So these are all things that you should have seen before. Okay? So if I add some amount of barium hydroxide, which is a strong base, now that's important because it means complete dissociation. That's important. Oh boy. Complete dissociation. What is the concentration of hydroxide ions in solution? What about the concentration of hydronium ions in that solution? Well, the first thing that I'm probably going to do is I'm probably going to write the reaction, right? Barium hydroxide dissociates into barium ion plus 2 ions of hydroxide. Okay, so I'm given this information, and I'm asked to find the concentration of hydroxide ion. Okay, so what I'm really looking for is moles hydroxide ion per liter solution. All right, now I'm actually given enough information kind of about both of these. I'm given information about the moles of barium hydroxide, and I'm given the volume of the solution, which in this case, nicely enough, was 1 liter solution. So the only thing that I really need to do is I need to convert these moles of barium hydroxide to moles of hydroxide ion. Okay? So just using the mole ratios, I know that 2 moles hydroxide ion are to 1 mole barium hydroxide. Okay, so I can solve for that with 2 sig figs, 5.0 times 10 to the minus 5th molar hydroxide ion. All right, now, so that's hydroxide. Well, what about hydronium? Hydronium doesn't appear anywhere in this solution. Oh, well, this is a solution in water, right? This is a solution made in water, which means that this auto-ionization is happening in water. Now, by adding barium hydroxide, I've increased the amount of hydroxide ion, but that doesn't affect Kw. So I still can use Kw equals concentration of H3O plus times the concentration of hydroxide ion. I can solve for hydronium ion is Kw over concentration of hydroxide. That's 1.0 times 10 to the minus 14 over 1.0 times 5.0 times 10 to the minus 5. Okay, and when I plug that in my handy-dandy calculator, I could do this in my mind, but you will undoubtedly be doing it in your calculator. I get 2.0 times 10 to the minus 10 molar. Okay? Now again, I need to add my unit in because this is a concentration. All right? So those are the kind of problems that you might see in the master doc, the kind of math problems today.